Hello students. Okay, I am repeating the lecture of equipotential surface which we have already studied. You know equipotential is divided in two words. Equi means equal and potential is potential. So a surface on which the potential is equal everywhere. So writing the definition, a surface at which potential is same everywhere is known as equipotential surface. Suppose now as you have written the notes, you might be knowing the formula for a potential at any point. That is equals to kq by r, where q is the charge due to of that potential, due to which the potential is r is the distance from their point. Okay, suppose we take a charge over here. Let us take capital Q. Okay, now if I want to find potential on this circle, suppose the circle has the radius of r. Okay, then the potential at this point, let it be v1, will be equal to kq by r, because the charge is q and distance is r. Suppose let us say I want to find a potential over here. Let us take this point v2. Here again q is the charge, once again the same charge, and distance is once again r, so it will be kq by r. Suppose I take another point over here, again radius is r. Let us take this point v3, that will be equal to k, once again the charge is same, kq by r. Similarly, if we take the potential over here, let us take this point 4, let me name it v4. Okay, the potential at this point will be equal to k, charge is q, distance is 1 again r. Okay, as it is radius is equal on any surface from the center. Okay, so if you find the potential at any point on this surface, okay, let us take infinite number of points. If you take infinite number of points, the potential at each and every point will be equal. Okay, so I can write v1 equals to v2 equals to v3 equals to v4, which will be equal to kq by r. So I can say that this surface, this circular surface, is equipotential surface. When you assume this in 3D, let us assume a tennis ball. Okay, there is a tennis ball. In the center of the tennis ball there is a charge q. So the surface of the tennis ball will be an equipotential surface due to charge q. Okay, so it is always in 3D. So I hope this is very clear. Now suppose I have a point charge over here. Suppose this is 1. Okay, now suppose I have another surface, that is let this be r1, let this be r2. Okay, so this becomes a equipotential surface, whereas this also becomes an equipotential surface, and number of spheres that will be over it will become the equipotential surface. Suppose this is potential having 10 volt, then this will be say 8 volt. As we go away from the charge, okay, as we go away from the charge, the potential goes on decreasing, because we know as we reach infinity the potential becomes 0. So as you go away from the charge, the potential will decrease. Suppose there is another sphere. Okay, suppose there is another sphere, let us name it r3, of radius r3. Then this surface will also be an equipotential surface having the value that will be less than 8. Suppose let us say it is 6 volt. Okay, so all the spheres having a concentric charge will all be an equipotential surface. Okay, all concentric spheres with same charge at center will form equipotential surface. Okay, I hope this is very clear to you all. Okay, once again I'll repeat it very fast. Suppose there is a charge at the center, and on the radius of the circle, suppose we need to find the potential at different points. So finding potential at any point, the formula we know that it is v equals to kq by r. Now finding the formula at any point on the sphere will always be equal to v is equals to kq by r, because the charge remains constant and the distance from the charge also remains constant, that is radius, as it is in sphere. So potential of any of this point will always be kq by r. So this is known as your equipotential surface. Similarly, if I make a bigger circle over here, that is in this case, you can see as we go on making the spheres with same center, okay, each and every point will have same radius, so it will make a equipotential surface. I hope this topic is very clear to you. Still, if you want to see another example, we can see. Okay, suppose we have a line charge. Okay, now if we find we have a cylinder over here. Okay, now here also you can find equipotential surface, where in this manner. Okay, here always it will be radius r, so potential at this point will be equal potential at this point. So similarly, in whole of this line, all the potential will be equal. Here if I say this charge is q, this is r, so v will be equals to kq by r. Okay, kq by r. Okay, similarly this side also. So the curved surface of the cylinder will always be an equipotential surface. Now suppose similarly in this also, suppose let us say this is a charge having a small cylinder. Okay, similarly here if I increase the size of the cylinder, okay, this will also form a equipotential surface. Okay, because the radius will remain again the same. So similarly, as it was in sphere, same it can be in the cylinder also. All this makes an equipotential surface. Okay, so now I shall rub it out. Similarly, we had tried for an whenever there is a uniform electric field. Okay, I had given the example during the lecture. Making a surface over here, this will also form an equipotential surface. Okay, this also forms an equipotential because the potential on this surface will also be equal. Okay, I hope this is very clear to you all. Now we shall move towards the properties of equipotential surface. Properties of equipotential surface. First property is potential difference on any point on an equipotential surface will be 0. Potential difference at any point on equipotential surface is 0. Why? Because of definition. Potential difference at n, if suppose this is an equipotential surface, then potential at any 2 point will always be equal. Suppose say A and B, then potential between this point and this point will always be equal. VA will be equals to VB, so VA minus VB will equal to 0, or VB minus VA will be equals to 0. So at any point the potential difference will be equal to 0. Okay, I hope this is very clear to you all. Then we'll move towards the second property. What does the second property say is that no work is done by electric force in moving a charge on equipotential surface. Okay, first of all let us understand what this wants to say, then we'll understand how it works. No work is done by electric force in moving a charge on equipotential surface. Suppose this is an equipotential surface, a charge needs to be moved from here to here, then no electric force or electrostatic force will work on it to move the charge from point A to B, because this is an equipotential surface. Let us understand how this will work. Okay, suppose we want to move from here to here. Now we know work done by electric will be equal to minus of work done by external agent. Okay, if the that is the definition of potential, that work done by external agent should be equal to the work done by electrostatic force. So here we know that V equals to W external upon Q, that is charge. Suppose we take Q, work done by external agent per unit charge or per charge. So here, but the potential difference is 0, because as we have seen in the previous property, potential difference on an equipotential surface is always 0. So minus W external will be equal to 0. This Q will go on this side. Suppose, let us say, I will take one more step. Hope this is visible. Yeah. So W external will be equal to 0. Now W external is equals to minus of work done by electric. So if work done by external force is 0, then work done by this will also be equal to 0. Okay, so electric force will be also be 0. So the amount of force required to move from A to B, if it is an equipotential surface, then the electric force required will be equal to 0. Okay, from here we can say net electric force required to move any charge will be 0 on an electric potential surface. Okay.